Hello everyone. In this episode, I want to talk about the cycle decomposition. In the previous episode, I talked about the cycles and the disjoint cycles. And the cycle decomposition means that there is a way to denote any permutation in a product of disjoint cycles. So let's look at the definition here. It says that for any permutation sigma in the symmetric group Sn, we can write sigma as a product of Ci's, which it is C1 times C2 times C3 until Ct for some integer t, and those Ci's are disjoint cycles. Okay, and then we call this product of Ci's, which equals to the sigma is the cycle decomposition of the permutation sigma. Okay, and one thing you should be careful is that because the Ci's are the disjoint cycles and the cycles are permutations, and then permutations are bijections, so the operation between bijections are just the composition of maps. So here the product of cycles does not mean the multiplication like those multiplication of integers or real numbers. They are actually the composition of maps. So this is the cycle decomposition, and we can look at an example for at first. So for example, let's look at the permutation in symmetric group S4, which permute the 4 elements 1, 2, 3, 4. So it maps those 4 elements to itself, and if the sigma looks like this: 1 to 2, 2 to 1, and 3 to 4, 4 to 3, like this, then the permutation sigma, we can see that if the permutation is applied to 1, we get 2. If it applies to 2, we get 1. So actually we can write the cycle like this. It permutes 1 to 2 under the sigma, 2 to 1 under the sigma, which is equivalent to say that 2 go back to the first element 1 here. So it's like this, and this is the cycles. It's a cycle as we saw in the previous episode. So it means that when sigma apply to 1, maybe we can do this, apply to 1, it is the cycle 1 and 2, like this. So this is like this just means the cycle applied to the integer 1 here. And actually if the cycle applies to 2, it is the same. We start at 2 and goes to 1, and 1 will go back to 2. So it means no matter we apply the sigma to 1 or 2, it is this cycle 1, 2. And then similarly, if we apply sigma to 3, we get 4. We get a 4 here, and sigma applied to 4, we get a 3 back. So it means the sigma is equal to like sigma applied to 3 and 4, it is equal to the cycle 3, 4. And we can see that when we apply the sigma to a number, integer in this set, we can cyclically permute some integers in the set. And then we claim that the sigma is actually equal to the product of those two cycles, which is 1, 2, and 3, 4. And those two are disjoint cycles. And because we said that in the previous episode, the disjoint cycles are commute, so it means that it is also equal to 3, 4, 1, 2. So we can change the order of those cycles when we do the multiplication, or we mean that the composition of those two cycles. So the sigma can be written in this way, and this is the cycle decomposition for this sigma, and we can verify it. So for example, if we apply sigma to 1, it is equal to, let's use the first like notation here. So it is equal to 1, 2, 3, 4, apply to the number 1 here. So those two things are just the like the denotation of the sigma here. So for this operation, which means that we can just apply the second cycle in this cycle decomposition to this input number first. So it is equal to 1, 2, then 3, 4, like this, apply to 1. So we do this part first. So this equals to, because 1 is not in this string of integers, so according to the definition of cycles, this cycle should fix this integer. So it means that this 1, 2 does not change. This we get a result. This equals to 1 here, so we get 1 here. Then the equation becomes to use the cycle 1, 2 to apply on this integer 1. So this cycle 1, 2 will move the 1 to 2, so 1 to 2 like this. So we will get a 2 here, and this is same as what we have in the for the permutation. When we just apply 1, we get 2. So we can show it in the in this diagram as well. So 1 goes to 2. And then if sigma applied to 2, it is equal to 1, 2, 3, 4, and apply to 2. And similarly, we do this part first, and because 2 is not in this string, so this part is equals to 2, because this cycle fixes this integer 2, and then we get 1, 2, and apply to 2, which, so this 2 give it to the first 1, so we get a 1, and this is like equivalent to we mapped 2 to 1 in this diagram. And then if we look at 3, it is equals to 1, 2, and 3, 4, apply to 3, and this part is, we do this part first, and 3 is in this string, so 3 goes to the next number 4, so we will get a 1, 2, apply to the result 4 here, and because 4 is not in this string, so we get 4 at the end. So just like 3 is go to 4 in this map. And finally, when we apply the sigma to 4, we will get a 1, 2, 3, 4, and 4. And here this part is equals to 3, and we get 1, 2, apply to 3, and this cycle fix 3, we get 3. So it means 4 goes to 3 as in this map. So this shows that this cycle decomposition equals to the permutation we are we defined here. So it means that we can use this cycle decomposition, which is the product of disjoint the cycles, to denote this permutation. Okay, but this is just an example. But if we want to show that for any permutation this is still true, we can show this by those 3 steps here. Those 3 steps. The first step, we need to show that sigma acts on any integer in the set A from 1 to n as a cycle, just as we show in the example that when we apply the permutation on any integer in the set, we can cyclically permute some integers like this. And the second, we want to show that the sigma acts on different integers as the same cycle or disjoint cycles. So it means that for example, in this example, if we use sigma to apply on 1 and 2, we are the sigma just behave like the cycle 1, 2, this cycle, and it means for those 2 different integer 1 and 2, sigma behave like the same cycle 1, 2 here. But for like 3 and 4, it behave as a different cycle 3, 4 like this, and this cycle is disjoint from the previous cycle 1, 2. So this is the second step. The third step is the permutation sigma is the product of different cycles, and those cycles are actually disjoint because of the second step. Those cycles should be disjoint. And okay, so the last one is just like when we write the cycle like this. And now let's show them one by one. So at first we want to show that sigma act on any integer as a cycle. So 1, the sigma act on any integer as a cycle. To show this, we can write that for any integer, maybe a1 is an integer in the set A. Then we can just draw a diagram like this. A1, if we apply the sigma, we will get A2, which this means that sigma A1 equals to A2. Okay, then we apply the sigma on A2, we will get A3. This means sigma A2 equals A3 like this. So this in this way we can write a chain of integers which we like repeating the permutation, we can get those chain of integers. Okay, so maybe let's write it in a more clear way. So we can start from any integer A1, then we go to A2, then we go to A3 after we apply the permutation, and it will goes to some a maybe k for some k, and then a k plus 1, and that goes on. And here this k, we say it is the first, the ak is the first or the last integer which makes the integers a1, a2, a3 until ak disjoint. This is the last integer, make those integers disjoint. Not disjoint, make them distinct. And this also means that the ak plus 1 is the first integer which is a repeated integer, which repeat some integer in this for this set of a1, a2, a3. So this is always true. We can always find this ak because a is a finite set. So we cannot go let this chain go forever without repeating any integers, because we eventually will exhaust the elements in the A. So at some point we will start to repeat some integers we have like it has been appeared before. So it means this ak, the last integer, make the first k elements distinct, is always always there, always exist. Okay. Then after we define this, because this ak plus 1 repeats some element in this part, so we can say that we can rewrite it like this. Move this part a little bit. Okay. We can say aj, it equals some aj here. Aj is before ak, and then looks like this. So equivalently, we can say that ak is go to aj, like go back to aj here. Okay, and then we can remove those. So it's like this. And then there are two situations. First, if j equals does not equal to 1, which means aj not equal a1, then what will happen is that aj is equal to sigma ak, because after we apply sigma, after we apply sigma, ak go back to aj, and also aj is also equals to sigma aj minus 1, because at the first time aj minus 1 is here. Aj minus 1 maps to aj under the permutation sigma. But because ak is the last integer, makes those numbers distinct. So ak should be distinct with aj minus 1. Ak does not equal to aj minus 1. And this will lead to a contradiction, because the sigma is a bijection. Bijection means it's a one-to-one map. So if we have those like sigma ak equals to sigma aj minus 1, this should give us ak equals aj minus 1, but actually ak should not be equal to aj minus 1, so this gives a contradiction. So which means j cannot be not equal to 1. Okay, then the second condition is if j equals to 1, and this means that the ak is mapped back to a1, and this is possible because a1 initially we don't have anything mapped to a1, so we don't have the problem in this case, which we have two distinct integers mapped to the same element a1, which give us a contradiction. And here we don't have anything mapped to a1, so we can allow ak to map to a1. So this is valid. So this situation is true. And now because we only have those two situations, so you can see that we for any integer, if we repeatedly apply the permutation on the integers, then we will get a chain which is a circle like this, and this circle just means that the permutation permutes those elements as a cycle. So this shows that sigma act on those integers. It will behave like a cycle, like a1, a2, ak, like this, because this just a cycle if we use the permutation on those integers. And this just what we want for the first step. So sigma act on any integer as a cycle here. Okay, so then the second step is to show that sigma act on different integers as the same cycle or disjoint cycles. So so first, as we show in this, the first step, we can write the integers permuted by the sigma as a chain like this. And if we consider the at first we have a chain of a1, a2, a3, and aj until ak. Then if we consider integer aj, which is inside this chain, then aj will give us if we draw the chain like this, what we will get is, because aj the next after apply the sigma on aj, we will get aj plus 1 because as we defined, the aj plus 1 is the next integer here. Then we will get aj plus 2, and then until ak, and the ak will go back to 1, a1, and the a1 will go to a2, and that goes to something, and eventually we'll go back to the aj here, right? So it means that no matter what integers we picked from this chain, and we apply the sigma, then the chain we will get is still the original chain here. The difference is just we begin from a different integer, but because it's a cycle, like any integer can be the first integer. So it means that when we apply the sigma on any integer in this chain, the permutation acts as the same cycle. So which is what we see here. So for some integers, the sigma act as the same cycle, and so this means sigma behave like a cycle A1, A2, AK, just the same cycle we show here. But if we consider something called B1 not in this chain, then what we get is we want to show that in this case we will get a disjoint cycle, and we can show because at first we have A1, A2 to AJ to AK like this, and then B1 we start from B1, we get B2, get B3 to B maybe M, and so we the B1 is not in this cycle, so B2 should should not be in this cycle as well. If this we want to show it's disjoint, so actually we can see that for some BM in this chain, if we assume some for the some BM, the BM is the last integer in this chain, which is not equal to any integer in this chain of A1, A2 until AK. Then it means that the next integer in the BM will be equal to some element in this the first chain, and if this is true, what we will get is that we will get like similar as the first case, first step, we will get AJ equals to sigma BM, because BM will map to AJ, and also equals to AJ minus 1, because originally AJ minus 1 here will map to AJ. So because BM is the last integer, which is not in this the first chain, and then the it means the BM should be be different from the AJ minus 1, and but because sigma is the bijection, so this equation will give us BM equals to AJ minus 1, which gives us contradiction, because those two should be different according to the definition of BM. So it means that we don't have the last integer which is not equal to the any of them. So there is no such last integer to have this property. So it means we will never have any integer in this chain is mapped to some element in the first chain. Then it means that anything in the second chain will be different or disjoint from the first chain. Then we can, if we consider the second chain independently, we will also get the like a circle like this, which when we get some B, maybe S, it will go back to the first one, which is also a cycle. So we will get another cycle is B1, B2, Bs, which has does not have any integer is equal to the integer in the first cycle. So this means this cycle is disjoint from this cycle A1, A2 until AK. So those cycles are disjoint, and this is true for any two cycles if they have different integers. So, and this is what we want for the second step. So for different integers, they form different disjoint cycles. And for the last step, we want to show that the permutation is a product of disjoint cycles. So, sorry. The third one. And for the third one, we can show it in a constructive way, in which we can construct such product of cycles, and take this cycle, take the cycle as we used in the previous two steps. For the cycle sigma, when we apply sigma to any integer in the set of A1, A2, A3, or until AK, any of them, we will get a cycle, this cycle A1, A2 until AK. So sigma apply to the set A1, A2 until AK, we will get A1, A2 until AK. Sorry. AK. And then we have this one. Then we pick B1, not in this set, A1, A2 until AK. Then sigma apply to the B1, or some apply to B1 first. Okay, we will get B1, B2, maybe we call it K2. Okay, we will get another cycle which is disjoint from the second cycle as we showed in the second step. Then we can apply pick maybe C, maybe not use C, maybe use D1, not in A1 until AK, union with B1 until BK2. Then sigma apply to D1. It will become a cyclic D1, D2 until DK3, like this. Then we can continue this this process until we cannot find any element. Maybe until all elements in A are used. So it means that there is no element left like all elements are in like some cycle we have built here. Then sigma can be written as A1 to AK, B1 to BK2, and D1 to DK3 until some maybe E1 to EK, some maybe S, maybe T here. Yeah. Okay. So like this. So those are disjoint cycles here, and the permutation can be written in those disjoint cycles. And we want to show this is true because if we apply, for example, cycle to something called maybe F3, maybe like this, or not F3, maybe for example D3 here, just an example. Then because those are disjoint cycles, so D3 only appears in one of the cycle, which is this cycle, the cycle of the D's. So for the any cycle like to the right of this these D cycles, they don't have this D3 in their notation of the string of integers. So according to the definition of cycles, those cycles just fix this cycle. So what we'll get is A1 to AK, B1 to BK2, and D1 to DK3 apply to D3, because all of those cycles on the right side just fix D3. So after we apply them to D3, we get D3. And then this cycle maps D3 to D4, so we will get D1, DK, B1 to BK2, and D4. And then because D4 is not in those two cycles, so all of them fix D4, so the final result is D4. So it means sigma applied to D3 is equal to D4, which is the same as what we define for the sigma, because we say that sigma can permute the D1 cyclically, like those D elements cyclically by D1 mapped to D2, D2 mapped to D3, and D3 mapped to D4. So this means the sigma can actually be written in this form, and this is the cycle decomposition for the permutation sigma. Okay, so until now we have shown that for any permutation in the symmetric group, we can write it as a cycle decomposition, which is the product of disjoint cycles. And hope you can enjoy this episode, and see you next time. Bye.